Hello, this talk is about data assimilation assisted by machine learning for digital twins in welding operations. The digital twin involves complex thermomechanical equations. This work is related to the PhD thesis of Pablo Pereira Alvarez, who is supervised by Pierre Kerfredan and myself. This thesis is funded by EDF. Prior focusing my talk on welding operations, I'm presenting some motivation for using more machine learning in engineering. We are developing a general framework on manifold learning for digital twins in mechanics of materials. Application to welding is one of the possible applications of this framework. There is three main factors that make machine learning very interesting for engineering applications. Material imaging and process imaging made huge progresses in terms of resolution, but also thanks to the development of X-ray computed tomography, infrared camera, and so on. Such observations can be used to feed numerical modeling. Today, supercomputers are available in many universities and companies. So high-fidelity modeling is only a matter of time, but it is possible. Thanks to that, we better understand the effect of various deviations that appears in real time and experimental data. On the top of that, these last 2 decades, machine learning, especially for image transformations and computer vision, has become more efficient and robust. And we all know that Python libraries are freely available for that. In many industrial sectors, engineers have to design or exploit complex systems where decisions are supported by numerical models that have many parameters. This is termed model-based systems engineering. Here, physical parameters are denoted by mu. These models have an informatic representation in specialized informatic platforms. In these platforms, we find workflows that connect CAD to the solution of partial differential equations by using the finite element model, for instance. Today, manufacturing processes are supervised by using imaging techniques. Hence, the construction of image-based digital twins for manufactured components is becoming an interesting issue in industry. In this talk, input images for numerical models are considered as parameters, and these parameters belong to a high-dimensional ambient space, P. Therefore, workflows transform both observational data and simulation data. These data both belongs to high-dimensional space that are also ambient space when considering simulation data and observational data. The definition of a digital twin have been proposed by Ryckelynck and Stargell in 2012. The digital twin integrate ultra-high fidelity simulation with the vehicle's onboard health management systems, maintenance history, and all available historical and fleet data to mirror the life of its flying twin and enable unprecedented levels of safety and reliability. Here, vehicle must be understood as a real instance of a system or a mechanical component. Without any limit on computing resources, we would like to develop digital twins where observational data are digital images. The computational complexity depends on the dimension of both the solution space V and the parameter space P. V contains all the fields that a mesh can approximate. P contains all the possible observations that a camera can observe. Solution space and parameter space are so huge that image-based mechanical modeling is too slow for practical application. We need reduced digital twins to get fast predictions. In that context, we developed a manifold learning approach to image-based digital twin. The solution space and the parameter space are sampled by simulation and observational data. These data belong to ambient spaces that are usually too generic. In most cases, the data don't fill the entire ambient space. This is true for digital images, for finite element approximations, and for most numerical schemes. For instance, on a digital image, we can see animals or mechanical components. It's very generic. Manifold learning aims to learn a sharper numerical representation for the space filled by the data. It aims to capture the dominant correlation between the data. We assume an underlying regularity of the data and a relevant bias in the training data. The proposed method for data assimilation starts by manifold learning in order to restrict the data assimilation to dedicated manifold. Some manifold learning algorithms are fine for data visualization in a space of small dimension. Here, we need a mapping back to the ambient space, especially for prediction purposes. So we restrict our attention to manifold learning methods with a mapping back to the original ambient space. Hence, we have three well-known approaches to manifold learning: the principal component analysis, PCA, autoencoders, and local PCA techniques. To my knowledge, PCA was first used for data-driven weather prediction in 1956 by Lawrence. Under complete autoencoders, on the left, are well-known neural networks for dimensionality reduction of data by using latent variables. In the center of the autoencoder, we find a layer of latent variables. On the left, an encoder transforms the input on latent variables. On the right of the latent variable, the decoder transforms a latent variable as an output in the original ambient space. Autoencoders and PCA are trained by self-supervised machine learning. They are trained to replicate the data similarly to the identity function. So no label is required, and it can be easily applied to a large volume of simulation data. Let's go through now to the data assimilation for welding monitoring. In a high-fidelity approach to data assimilation, the solution of PDEs is constrained by observational data. In a sense, a calibration step of the model is coupled to the solution step of the PDE, but it is very slow. We propose to learn a data-driven manifold as a meta-model for parametric PDEs. The novelty here is related to the huge dimension of the parameter space. It can be more than 1,000. Hence, a multimodal manifold learning has been developed. The multimodal manifold learning involves a manifold learning for both the solution space and the parameter space, which contains the observational data of a digital twin. So we consider multimodal data D and U, and we try to learn from this data D and U a multimodal manifold. The solution manifold is therefore a subspace of the multimodal manifold MM. But we assume that the parameters for the reduced solution space is the reduced variable obtained from observational data by using an encoder E index D. We assume that the latent variable alpha is obtained from observational data by using an encoder E index D. Here, alpha is the latent variable for the multimodal latent space. On the left, we have a schematic view of the meta-model used for a fast data assimilation. After the training of the manifold, we observe the data D. Then we compute the latent variable alpha, and then we can forecast an approximate solution U tilde for the PDE. Such predictions can be performed in real time. Hence, a multimodal manifold has been developed for process monitoring of welding operation. When a crack appears, the process has to be stopped and restarted. Hot cracking phenomena can be predicted in real time if we have a fast prediction of the maximal principal stress during the welding process. The observational data is a temperature field observed on the surface by an infrared camera. We can see an example of such temperature field on the left. This temperature field can be transferred on a mesh related to the thermomechanical PDE. We also have some process parameter as additional observational data. These parameters are denoted by mu. The digital twin output is the three-dimensional temperature field and the full stress field. We can see an example of this stress field on the right. So the multimodal data are the temperature field, the stress field, and process parameter. but we add also parameters related to the heat source. These parameters of the heat source are denoted by theta. They are not observed directly during the process. The multimodal manifold learning is performed by a local probabilistic PCA. This probabilistic formalism gives access to an error estimation as shown below for the prediction of the stress field. The local probabilistic PCA is set up by introducing a prior probability. Let's make things simple by using a schematic view of the local PCA. We start by using one high-fidelity digital twin of the welding operation. The local approach is mainly motivated by the fact that a global reduce basis fails to reduce the data observed in welding operation. This is due to the motion of the heat source. Hence, the position of the heat source is a parameter. Thanks to the motion of this heat source, the high-fidelity digital twin gives several points on the latent space. This is the red points here. Each point is related to one position of the heat source. We don't have big data for observational data, so data augmentation is necessary. A physics-based augmentation has been performed around the true original data by using the parametric PDEs. Now I give more details on the mathematical formalism. The multimodal data of the temperature field, the stress field, the process parameter mu, and the heat source parameter theta. The observational data are the surface heat temperature field and the process parameter mu. So the multimodal data are denoted by the vector S. It's a very high-dimensional vector, as we can see. After data augmentation, we have created 160 clusters of heat source positions. On each cluster of multimodal data, we have computed a local probabilistic PCA. Here, in equation 2, we can see the local latent variable alpha k, where k is the index of the cluster. According to Bishop, 2006, the solution of the maximum likelihood problem has the following clause form. The radius basis phi k is computed by using a singular value decomposition. Here, sigma s is the unexplained variance. In equation 3, the blue part is specific to the probabilistic approach. Usually, in PCA, we don't have this blue part in equation 3. We assume that the multimodal variable follow a multivariate Gaussian distribution as a prior distribution. The mean of this distribution is denoted by S bar. Its covariance matrix is denoted by capital sigma Sk. Once we have new observational data, we can set up a posterior probability. The posterior probability accounts for a Gaussian model of measurement error. The standard deviation of measurement errors have been calibrated by using thermocouples and infrared camera data. If we restrict observation to temperature higher than 350 degrees, the standard deviation is 18 degrees. The posterior probability follows the Bayes theorem. The posterior probability on latent variable alpha is conditional by the observation of D. Here, P of alpha k is the prior distribution related to the training set of data. We assume that parameter mu are deterministic. The equations of the posterior distribution are the following. The latent variables have a multivariate Gaussian distribution. The expectation maximization gives the mean of the latent variables and the covariance matrix in equation 6 and 7, respectively. Hence, we get the mean and the covariance matrix for the multimodal variable. In practice, we only use the diagonal of the covariance matrix for error estimation. This diagonal is a high-dimensional field in the ambient space of the training data. Here is the numerical results. Let's consider a given each source position of index k. We can check the prediction of the observed temperature on the line of the specimen. The estimation obtained by the local probabilistic PCA is in blue. The data from the camera are in red. The confidence interval is small for observational data, and this interval is consistent with the discrepancy between the prediction and the observation. For the same each source position, we have compared the predictions to a high-fidelity digital twin of the experiment. The temperatures simulated by the high-fidelity digital twin are in red. In figure A, we have the camera side. In figure B, it is the side of the heat source applied to the specimen. Thermal conductivity is not consistent here between the high-fidelity digital twin and the proposed metamodel. And we can see that the confidence interval is smaller on the camera side. Surprisingly, we have more consistent results on stress prediction. Obviously, we have large confidence interval on stress predictions conditioned by temperature observations. But the confidence interval is reasonable for practical process monitoring of hot cracking risk. We have developed more results on multimodal learning by using multimodal autoencoders. I would like to say just a few words about that. For instance, we can predict defect harmfulness when voids or cracks are observed on tomographic images. Dedicated reduced digital twins have been developed for that by Hugo Launay. These predictions for defect harmfulness are using multimodal autoencoder, where one modality is related to the image of the defect and other modalities are related to mechanical predictions. My conclusion is that we propose reduced digital twins that are based on digital image. Data augmentation is a key point. We assume to have accurate physics-based models for that. Multimodal approach to model reduction is a nice framework in case of huge parameter space. And we have theoretical results available in case of piecewise linear approach like singular value decomposition or local probabilistic PCA.